in two of the setups, you guys have a meter stick that's off-centered. You know, the first example of that is something where the instead of being clamped at the 50 centimeter mark, it's clamped at the 40 centimeter mark. So when that happens and you have your fulcrum here, what's happening is that there's more weight on this side than this side, so it's going to rotate like that, in this case how I have it drawn clockwise, and that's because the meter stick is an object with weight, and we treat it as if its center of mass is where all that weight is directed. So you get a force of gravity directed downwards right there, and that's really the only force we look at, and then that force would in turn generate torque, and so that would be a negative torque, which is why it would go clockwise. But what we ended up doing was we said, well, let's hang some sort of other weight on the other side, and that would give us a different force of gravity there, and then that would be counterclockwise. So it's pretty easy now. You still have two torques that need to balance out, and you just set the net torque equal to 0. Essentially, the torques end up being equal to each other in size, and then you can figure out, you know, what the theoretical location of this weight should have been in order to balance out those torques. The other case in which we have something that's off-center is the one in which you have the 100 gram weight on one end and the 200 gram weight on the other end. Now, if this were centered at the 50 centimeter mark, it's clear that the 200 gram weight would win. But what we do is we hunt for a position in terms of where to clamp it, and that ends up balancing out your two masses there. So it would have to be closer to the 200, farther away from the 100, somewhere there. And trying to experimentally find that is not difficult at all, because all you do is kind of slot it until it's balanced. But trying to theoretically calculate where that position is, there's a little, you know, math trick that we need to do. So I think what I told you guys was this is located at 1 centimeter, this is located at 99 centimeters. But you know, just for the sake of simplicity, let's just actually just say this is 0 and this is 100. I'll let you do that in lab just because it'll make this a lot easier to see. So basically, you know, we need to figure out the theoretical location of that fulcrum. And one of the things that a lot of people might overlook is that you actually have the meter stick contributing to this. So you have a force of gravity from the meter stick, you have a force of gravity from the 100 mass, you have a force of gravity from the 200 mass. And you got three torques balancing out each other. These two are counterclockwise, this one's clockwise. So when we write out the torque expression, it's sigma tau equals 0. And we have no idea where this is supposed to be located. So it seems like we have three unknowns in terms of how far away things are from the point of pivot. We don't know how far this is from the pivot. We don't know how far away this is from the pivot. We don't know how far away this is from the pivot. But if you take a look, let's label the figure up here. I'm going to call this distance x. And that's going to be my variable that I ultimately want to solve for. Moving over to this distance here, it's related to x. So this is a meter stick, so it's 1 meter. Let's call this 1 minus x, because this would be this 1 meter minus this distance would give us that distance there. So that's 1 minus x. And then the trickiest one is probably this one here. We want to know what this distance is here. So we know that this is x, and we know that this is 0.5. So let's call this x minus 0.5. Now everything's in the same variable, three unknowns, but a single variable. So when we go through our clockwise torques, this is a 100 gram mass, which is 0.1 kilograms. Its force would be 0.1 times 9.81. How far away is it? X, that distance away. This one here, I don't know what the force of gravity of your meter stick was, or the mass of your meter stick, so let's just write mass of the meter stick. And then let's write 9.81, and let's write x minus 0.5. And this last one, it's a negative torque. That's a 0.2 kilogram mass, 9.81. and then 1 minus x. Now, you see that 9.81 appears in each term here, and there's 0 on the other side, so we can divide all sides by 9.81. And the instant you plug in your mass of your meter stick right here, now your only unknown is x, and you can theoretically solve for x, and that would give you the exact location of where this pivot should have been placed. So you'll be able to do the comparison based off of this. So that's a little math trick that should help you guys out in the lab today.